Hi guys, welcome to chapter 6. Today we're going to begin our notes for 6.1, and our first objective is we want to be able to construct a probability distribution for a discrete random variable. Okay, probability distribution is a fancy way of saying a table of the probabilities. Okay, so for instance, just before we get going, this right here is an example of a probability distribution. It's a table of probabilities. Okay, the big deal is that a discrete random variable means it has a countable number of possible values. You own 3 pencils or 4 pencils or 5 pencils. You have 0 siblings, 1 sibling, 2 siblings. There is 10 birds in your yard, 11 birds, or 12 birds, whatever it would be. It's a countable item, right? When you have a discrete probability distribution, then you're going to take those random variables and you're going to give them the numbers, and then you're going to also talk about the probabilities of those events occurring. So this example here, as we keep coming back and forth, is imagine selecting a U.S. high school student at random. We want to define the random variable x as the number of languages spoken by a randomly selected student. So you either speak a language or you don't, right? So with this, if we go with that discrete context, then you can have a student speaking 1 language or 2 or 3 or 4 or 5, according to this example. All right, the probabilities of that occurring, the probability of a student speaking 1 language is 0.63. The probability of a student speaking 2 languages is 0.295, and so forth, okay? So it is extremely unlikely for a student to be speaking 5 languages. Key concepts of a probability distribution is that the sum of all of your probabilities needs to add up to 1. So these probabilities here needs to add up to an exact perfect 1 each time. You also need to remember that the probability needs to be between 0 and 1. Okay, so if you have a negative in one of these spots, well, negative probability is impossible. So even though it might add up to a perfect 1, if you have a negative probability, then it's not a valid probability distribution. So if we want to do part A for this problem, we want to show that the probability distribution for x is legitimate. Keep in mind, you always need to identify what x is somewhere, whether it's in the problem or if you create it on your own. You need to say, like, let x equal blah, blah, blah. All right, if we want to show that this is legitimate, we're literally just going to show that the sum is 1. I should have written this ahead of time, sorry. Speed things up a tad. Right? It adds up to 1, so we're good to go. Right? Find the probability of 3 or more languages means 3 languages, 4 languages, or 5 languages. So again, you are not allowed to just have answers show up out of nowhere. You need to show, like, you can't just have this answer. You need to show where that answer comes from. Okay, I added up those 3 probabilities. Part C is saying make a histogram of the probability distribution and then describe what you see. So I've got my probability distribution here. I have the probabilities of my events occurring here, and I have the number of languages here, right? This really should be basically on the line. I just couldn't draw it that way, but 0.002 probability is pretty much nothing. So when you describe what you see, state the obvious, just like we did in chapter 1 when we did these graphs. When you state the obvious things here are most students only speak 1 language, over 60%, okay? And then between first and second, we have over 90%. 90% of students speak only 1 or 2 languages. 10% of students speak 3 or more, all right? Any of those would be good. This is a right skew graph you could use, all right? Any of those terms, good stuff. All right, so now let's talk about how to come up with them on our own. If we look at number 2, what is the probability distribution of the discrete random variable x that counts the number of heads in 4 tosses of a coin? So we want to let x equal the number of heads. All right, now keep in mind, if I talk about 3 heads, it could be T, H, H, H. It could be H, T, H, H. It could be H, H, T, H. It could be H, 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 T. Right? The order matters in which way they roll, just like dice, okay? Which way roll, flip, however it goes. If you have two options, heads or tails, to the fourth power, because we're flipping it 4 times, then that means that we have 16 outcomes. There is one way to get all no heads. There is only one way to get all heads. There are 4 ways to get 3 heads. If we go vice versa, if we have 1 head, it'd be the exact opposite if we just flip them, right? H, T, 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 H, T, H, T, 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 H, T. So there's 4 ways to get 16 heads. 4 ways to get 1 head, I mean. So far I've used 5, 10 of the options out of 16 if I added the numerators. So knowing that this adds up to 1, then that leaves this with 6 out of 16. You could also sit down and write them all out if you want. There would be 6 ways to get 2 heads, 2 tails, if you mix and match all of the ways they could go. All right, so if we want to know the probability of getting at least 2 heads, oh, also, you could convert these to decimals if you'd like, but if you convert them to decimals, don't round. So this would be 0.0625. This one would be 0.25, 0.375, 0.25, 0.0625. Keep them so it adds perfectly up to 1. So if we want to find the probability of at least 2 heads, at least 2 heads means 2 or 3 or 4. So I have 6 out of 16, I have 4 out of 16, and I have 1 out of 16. So my answer would be 11 out of 16. If I have at least 1 head, you could, for this one, just add up all of those, right? Because that's pretty easy to add your fractions. Or you could do 1 minus none. All right, that's what I did. I did 1 minus no heads. And that leaves me with all of the at least 1 heads added up together. But you could add 4, 6, 4, and 1, and you'd get the 15 as well. Alrighty, now, what do we do with this? Well, if we want to calculate the mean, the variance, and the standard deviation, and the expected value for a discrete random variable, this is a biggie, okay? This is a big deal. Your mean of your probability distribution can also be called your expected value. It can also be called your mathematical expectation. So a problem can mix and match these terms, and they're all asking you to do the same thing. On your formula card, it gives you the average, or capital E is the expected value. And what we do is we just do the sum of x times p of x. I'm going to walk you through it. I think it's going to make a lot more sense as you see me do a problem. Okay, so we're going to do x times p of x, x times p of x, x times p of x, and so forth. To calculate the standard deviation, we're going to use this formula that's also on your formula card. And I will walk you through it because it's a lot scarier looking than it is a process. Okay, so if we go back to the problem with the languages, one language is a 0.63 probability. 2 languages is a 0.295 probability. So to compute the average, what you do is you take the x and multiply it with its probability, plus take this x and multiply it with its probability, plus take this x, multiply it with its probability, plus this x with this probability, plus this x with this probability. That's what this formula was saying. Add up all of the x times p of x's. If you want, you could put like a parenthesis around it, if that is visually easier for you. Word of advice, type this line in one shot into your calculator. Okay, just type it all in at once rather than carrying little decimals around. Just type it in one big long calculation. So that means our average is 1.457 languages. All right. Your standard deviation, to compute your standard deviation, I do the variance first, which means you just get rid of the square root sign. Because remember, your standard deviation is the square root of your variance. So your variance is just what was inside. So here's how this formula works. Okay, you need this average that we just calculated. And we need to do, like, this right here is for the number 1. It goes x minus mu squared times its probability. So it was x1 minus mu, 1.457, squared. And then you multiply that with its probability, 1's probability. Then you do it again for 2. So the x is 2, and the probability is 0.295. So it'll be x minus mu squared times its probability. Then you do it again for 3. 3's probability was 0.065. So 3 minus mu squared times its probability. And you do it for 4, and you do it for the value of 5. I just ran out of space. That says 0.002. Again, type this entire line carefully into your calculator in one shot. Okay, just go slow, use parentheses, square, type, multiply by this, type the whole thing in, press enter. Do this now, okay? Like, don't just expect to wing it on test day, all right? Make sure that you're able to type this in, square, and get this answer. Okay, this is your variance. Remember, that's our symbol for population variance. So then to get your standard deviation, you're just going to square root that answer, and you would get this. If this were a free response question, you have to show this work. All right, you cannot just get this. And you guys know how much I love calculator shortcuts because I love to work efficiently. There is not one for this. If you find it, please share with the rest of the class. I have not found one in the TI Nspire. So yeah, if you find one, definitely let me know. Okay. All right. So what I want you guys to do is read this problem. All right. It's epic. All right. But we've got all these different things. So this is like when a baby's born, every baby gets an APGAR score. Sorry, I'm off the camera. Every baby gets an APGAR score from 0 to 10. And depends on how well they're doing when they're born. This is the best, right? 32% of babies have an 8. 44% of babies have a 9. Okay, 5% of babies have a perfect 10 of an APGAR score. If a baby had a really rough delivery and isn't doing well, it might have an APGAR score of a 0, 1, or 2, or something like that. But it's very unlikely for that to occur as it goes through. We want to find the mean, the variance, and the standard deviation. So for this particular problem, for me in class, if you had something this long, I am okay with you. So I have x times its probability plus x times its probability plus x times its probability plus I put ... and then wrap it up with the last one, x times its probability. Some of you are going to be just fine like looking at and plugging in your calculator, so I'm okay with you putting ... in the middle rather than writing all of that out. Some of you still might benefit from writing it all out, and that's okay too. Just kind of depends on your comfort level. All right. Try now. Type this in your calculator. You should get 8.128. Okay. So then when you set up this one, I rewrote the formula up here. It's x minus mu squared times the probability of that x. So 0 had a probability of 0.001 here. And this was the mean we just found. Plus 1 minus mu squared times its probability, 0.006. You would do this for 2 and 3 and 4 and 5 and 6 and 7 and 8, 9, and here's 10s. Your answer would come up to be 2.0656. So then when we square root this, we would get a standard deviation of 1.437. All right. Now, these aren't always written out for you. Okay. Sometimes we have to get them on our own. So for instance, if we have 1,000 tickets are sold at $2 each for a TV valued at $350, we want to know what the expected value of the gain, which is the same as saying the average gain. If a person purchases one ticket, and we want to do this problem from the eyes of the player. Okay, because in the eyes of the player, your gain and your loss is different than if you're the lottery ticket or the carnival or whoever's selling the raffle, right? If I'm running the raffle, everyone who buys a ticket is a profit for me. If I'm playing the raffle, then every time I buy a ticket is a loss for me. All right. So when we look at this, what you want to do is you want to set up your probability distribution. My money goes up here, my dollar value, and my probability goes down here. So for this particular problem, we have two categories. We have win and we have lose. I always start with losing. All right. If I buy a ticket, what happens to my wallet? I lose $2. So I'm out $2. All right, that's my money. If I win the TV valued at $350, what happened to my net worth, my wallet gain? I didn't gain $350 because I paid out $2 for my ticket. So my gain was really only $348. So it's my positive because yes, I got a $350 TV, but I paid $2 to get that. So I always start with my lose, and then I figure out how much my money is for winning. Then I figure out my probability of winning. What's my probability of winning? I buy one ticket, and there were 1,000 sold, which means what's my probability of losing? I have 999 chances of losing. This is probably where I'm going to be because I'm a very unlucky person. All right, and when it comes to lotteries and stuff. Once you've set up this, if it asks you for your expected value, it's asking you for your average gain. So your expected value is your average. We're going to multiply these, 348 times 1 out of 1,000. And we're going to add to that the -2 times 999 over 1,000. Yes, of course, you could just put minus here, but I'm really showing it's you add them together. You just happen to be adding a negative this time, okay, because it was negative in the problem. It's not usually subtract. It's not, the formula isn't subtract. Throw this in your calculator in one shot, all right, and then switch it over to money as a decimal because you don't want a fraction for money because that doesn't make sense. So here is my expected value. But what does that mean? Because you're going to be asked to interpret this. If you're asked to calculate it, you are almost always going to be asked to interpret it as well in a free response problem. So the interpretation is a player can expect to lose, or a player loses $1.65 on average each time they buy a ticket. She buys a ticket. All right, so yes, I know it's either you pay 2 or you win $350, but over time, let's say you keep having this raffle. Maybe student council was able to hold this raffle every week for a fundraiser all year. All right, if they were allowed to do that, they're not, but if they were allowed to do that, you could buy a ticket over and over and over and over again. So on average, over time, you're going to lose $1.65 each time you buy a ticket. You might win, all right, but you're probably going to lose most of them, okay? You might win once in a while, but you're most likely going to lose a lot of them, which is our average loss. So use pencil and try setting up number 8. So pause it, read it, see if you can figure it out on your own, and then come back. All right, we have our money, we have our probability, okay? You can win 100, you can win 50, but notice I'm putting them up high because that's not our money yet. Win 25, win 10, or you can lose. All right, now after each prize drawing, the winning ticket is returned to the pool of tickets. That's important because that's going to keep us with our probabilities being much simpler. What is the expected value if a person purchases 2 tickets? So if they're $1 each and there's 2 tickets, then that means that if I lose, I'm out $2. What happens if I win 10? If I win 10 but I paid 2, that means my profit is only a +8. If I win $25 prize but I paid 2, my profit is only 23. My profit is only 48. My profit is only 98. Okay. 500 tickets were sold. and I bought 2. So I have a 2 out of 500 chance here. Since the winning ticket is returned, that means that I again have a 2 out of 500 chance here, again a 2 out of 500 chance here, and again a 2 out of 500 chance here. Now, what's my probability of losing? My probability of losing is going to be what? Well, it's not 498. I've already had 2, 4, 6, 8 chances to win. So since I've had 8 chances to win, then I only have 492 chances to lose. Okay, because again, this has to add up to a perfect 500 out of 500. To find my average or my expected value, I would need to do 98 times 2 out of 500 plus 48 times 2 out of 500 plus 23 times 2 out of 500 plus 8 times 2 out of 500 minus 2 times 492 out of 500. Right? 2 out of 500, 2 out of 500, 2 out of 500. Put this all in your calculator in one shot. All right, and then our expected value will be a negative $1.26, which means every time you buy 2 tickets, you're expected to lose $1.26. Alrighty, so I think this is actually way long enough for now. So we will go over it. The rest of them are pretty quick to do together in class. So I think we're just going to do those together in class next time I see you. All right, good job today.